All right, so good morning, everyone. I have to say I'm very impressed with the turnout for the morning keynote. So I appreciate you all being here. So I'm guessing you're excited to learn how to build your own static code analyzer in Python. So a little bit about me before we get started. Thomas, can you turn off your mic?
I'll try.
Can we also start the timer on here? Okay. So a little bit about me. So I'm a software engineer at Bloomberg in New York City. I'm also the author of Hands-on Data Analysis with Pandas, which is a packed book. I don't know if that's out there, but maybe it is. I did my undergrad at Columbia University, and I did my master's in computer science at Georgia Tech. So I'm also one of the core developers of a tool called NumPyDoc, which does, amongst other things, the Sphinx extensions that are used to build the documentation using the NumPy style of docstring. And particularly that is because of my contribution of actually creating the pre-commit hook for using NumPyDoc to validate your code, that the doc strings are according to that standard as you're committing it. And that is a tool that uses static code analysis. So before that change, it was only running what is called dynamic code analysis. And so in this keynote, I'm going to share with you how you can actually do something like that, use static code analysis to build something on your code. So this is going to be a highly technical keynote, so I hope everyone had their coffee before coming in. And don't worry about taking tons of pictures of the slide. There is definitely going to be a good amount of code on there, but the slides will be public, and I will put a link in the Discord later on, so you'll have those at your disposal. So what makes a tool a static code analyzer? So it is simply a tool that analyzes the code, the source code, without actually running or executing it. And the main benefits of this are the speed. So this can be much faster than running dynamic code analysis because you're not actually running the code, right? And it's also portable because you don't need to run the code, you don't need to install it or its dependencies. So those are two huge benefits, and that also make it so that you can build it once and then use it on multiple code bases because it's not tailored to that code base. So how do you actually build a static code analyzer? As with anything, it depends, right? But the key here is that abstract syntax trees, which is what I'm going to talk about today, are a great place to start when you want to build one of these. So an abstract syntax tree represents the structure of the source code as a tree. And each of the nodes are then language constructs. So a module would be a node, a class would be a node, a function, etc. And then each of those nodes can have a single parent. Right? So if we have a particular class, it's a child of a module. It's not existing in multiple modules. And then parent nodes can have multiple children, right? You can have a class that has multiple methods, right? You can have a module that has multiple classes and functions inside of it. So let's see what an AST actually looks like. And we're going to start, and for the duration of this keynote, we're just going to use this simple code snippet as our source code. But obviously, you can imagine that we would be working with a massive code base that is much bigger than just this little snippet. So this is going to be our greet.py file. We have a class with two methods. And this is the AST behind that. So this is how this is actually being represented. We're not even going to use all of the nodes here to do the task here, and this is only a small subset of all the node types that are possible. So if you can imagine if you have some more complex code, you're going to have other node types that we're not seeing, like yields or different mathematical operations. So ASTs in Python represent syntactically correct Python code. So you can't generate an AST if the code has syntax errors. And this is because the ASTs are created by the parser as an intermediary step when we are compiling source code into bytecode. And that is what actually has to happen in order for it to run. And we have access to this in the standard library via the AST module. So let's take a look at how we would actually use the AST module. So we would start by reading in some source code. We need to have our code that we're going to analyze as a string. So however you go about actually obtaining that string, here's one way of doing it. You could, if you're analyzing something simple, just type it in the actual string you want to analyze, and we'll see that later as well. So here I'm using pathlib, and I have source code, which is just a string representing all the text that was inside that file. And then we're going to parse it with the AST module. So we import AST, and then we use the parse function in there, and we're passing in the string of all the code. And this gives us back, again, assuming that that code was actually valid Python. It is, and so we get back our tree, and if we look here, we see that it has type ast.module. So when we ran this code, we got back a tree. We get back represented as a single node, the root node of the tree, which is the module. And logically, this makes sense, right? We are giving it a module of code, and now it gave us a module as the root of that tree. Now, natively in the AST module, we have one way of visualizing, quoting that, visualizing what is actually inside. And this is handy if you're just trying to debug something really quick. It's obviously a little tough to read the layout here, but it's important to understand that this exists. So it's the dump function, and it has this indent parameter here where you can say just how far to do the spacing. So I'm doing it 2, and then it lets you see the nesting of all the items in the tree. So we see that the root of the tree is the module, like I was saying before. The module itself then has a body, so the contents of that module you can see is a list. Then the first item in that list is a class def node, so the definition of the greeter class. Then that greeter class has a body also, so then that's the list of the AST nodes inside of it. So we can see that we have a function def node, and that is the definition for the init method. We have the arguments for the init method, and then we have the body of what the init method actually does, again as AST nodes. We have a return type annotation if it was present, and then we have our other method. So that is pretty much the contents, and we will go through breaking most of these parts up and extracting information from there. So before we actually dive into building the tool, I did want to share some popular open source tools that you've probably used, at least some of these, and they actually use ASTs, and so you've been using them without realizing potentially. So linters and formatters like rough, which is in Rust but is still using an AST, and black, which is using ASTs directly in Python. Documentation tools like Sphinx and the NumPy doc validation hook that I mentioned. Automatic Python syntax upgrading tools. So like when you try to port your 3.8 code into 3.12 and there's changes in syntax, tools like PyUpgrade that help you do that are using ASTs. We have type checkers like MyPy, code security tools like Bandit, things that test coverage like Vulture and coverage.py, and also testing frameworks that are instrumenting your code, so Hypothesis and PyTest. Okay, so now we're going to go and actually build our static code analyzer. And again, our aim here is to build it so that we learn how to use the AST. And to do that, we're going to build a simple tool that is going to find missing docstrings and then suggest templates based on the code itself of what the docstring should look like. And we're going to do this using only the Python standard library. So tools may exist that do this already, and that is beyond the point of the keynote, right? We want to focus on how do we actually work with the AST. So again, our input will be this single module here, greet.py. And you can notice that there are no docstrings in here, but we do have type annotations. So if we're working with something small like this, right, you might be asking, is static code analysis really necessary? But the key thing to keep in mind here is that this is a toy example, right? We have one file. How many people have a code base that's one file that looks like that, right? Nobody. So and the reality is you have massive code bases or you have multiple code bases and you want to do similar checks across the board. And that's where certain approaches struggle to actually scale, right? Manually opening it becomes extremely tedious and error prone. Trying to do regular expressions just becomes absolutely chaotic. Trying to script everything so that you import and then check the doc strings one by one definitely works, but it then becomes something that you now have to install the code base, and it becomes very slow. You have to rewrite it every time you want to write a new code base. And so static code analysis gives us something that we can run on our code without executing it, right? And so we can use this on any of our code bases. And so this is the way to go. Okay, so before we dive into the code, we're talking about finding doc strings that are missing and suggesting them. And those of you who are paying attention will notice that all of the doc strings in the code I'm going to show you are non-existent. And that is on purpose, right? It's for space. There's simply no space to put doc strings on all these examples. But as a fun exercise afterwards, if you want to test this out, you can actually use the tool we're going to build on itself to actually add the doc strings in there. Okay, so let's talk about detecting missing doc strings using the AST. So we have two components that we need to figure out. The first thing is we need to figure out how to actually traverse the tree. And then the other thing is that once we're at a node that we actually care about, so something that could have a doc string, then we want to actually have a function that we can call that will tell us the doc string is missing or the doc string is present. And so we're going to start with that bit. So we're going to define this detect missing doc string function. And you'll notice I'm going to use the type annotations in lieu of having the doc string so that we can understand what types of nodes we're going to run on and what kind of output we would expect. So here, for detecting missing doc strings, we only care about 4 node types in the AST. So these are the only 4 node types that can have doc strings per the AST. So we have the module, the class definition, the function definition, and then the async function definition. And then to actually check if there is a doc string, the AST provides a getDocString function. This receives the node and will give back the doc string if it exists, or none if there is no doc string at all. So you'll notice the check here is we just check if it's none. So this is also a little layer of simplification that we have here, right? You could have a doc string that has just no text, but it's just physically there, right? Or it's just spaces. That's something that you could add on later as a more robust check than just looking at none. But for now, we will keep it simple. So if we enter in this block, then we're just going to we just have a print. So we're just printing, hey, this particular node is missing the doc string. So now we can start looking at the traversal, right? So for greet.py, this subset of the tree is the only thing that we actually care about exploring and looking at. So you'll notice it's 4 nodes. It looks rather simple. You might be thinking in your head how you would traverse the tree, and it's probably very trivial, right? But the thing is that traversing the AST becomes more complex when you have nesting and classes inside of functions, and whatever. It becomes untenable to try to write that yourself. And the good thing is that the AST provides a base class that we can use to easily do that traversal. And it's called the node visitor. So what we're going to do is we're going to subclass that. And then we are going to define the visit methods for each node that we want to do something on, something specific on. So for our case, we're going to define methods for each of the nodes that we actually want to check the doc strings on. And you'll notice that it's visit underscore and then node type. And if you recall, the node types were not in the same casing as this. So you're going to have some wonky looking function names or method names, and your linters will complain about it, but that is the way that these have to be written. And then once we have all that written, then we can actually use the visitor, and we'll call its visit method on the tree, and then the traversal will happen for us. So here's how that looks, right? We subclass our AST node visitor, as we're going to call this our docstring visitor. And then we're going to define 4 methods, right? We have 4 nodes that we want to visit: the module, the class definition, the function definition, and the async function definition. So you notice we have 4 methods. Again, note the casing. This is the syntax for this. And then for each one of these, we're just going to call our detect missing docstring function, and we're going to pass in the node itself. Notice that nowhere did we define that these methods actually should be called at any point. This will happen automatically. So now we can use this visitor, right? So we instantiate the docstring visitor. We call the visit method, passing it that tree that we read in earlier, which is the AST. And we get a result. It says module is missing a docstring. And while that is correct, the module is missing a docstring, we saw that there were 4 items that are missing the docstring: the module, the class, and the 2 methods. So something didn't happen correctly here, right? We missed 3 of those. So what actually happened here is that we didn't actually traverse the tree at all. We visited the module, and then we just stopped. We got stuck. And there's a reason we got stuck, but first we need to understand how this AST actually looks. So I've expanded now the smaller AST we had from before, and now you can see that we have several fields on each of these nodes. So the module had a body, the greeter class has a body, right? Function def has a body. Now, it's not enough just to explore the body. We actually have to explore all of these fields. So for example, this one right here, args, the args, that is itself a whole list, a subtree that can be explored. And so this is also why you wouldn't want to try to write a traversal algorithm yourself, and you would want to use the visitor, because there's actually a very simple way to fix what we did wrong here. And that's using the general visit method. So this is defined on the base class, and it's going to go and visit the child nodes for each of the node that we're currently visiting using the iter fields function that the AST provides. So that includes the body and then the args field that I mentioned, anything else that might have nodes that can be explored. And that makes sure that those are surfaced. And this is actually called automatically for node types that we don't create those methods for. But the problem was that once we created the method for the module, this was never called, and so the traversal stopped at the first node. So now we know how we need to modify our docstring visitor. We're going to add a visit helper method, and this is going to be called at each node we visit instead of just checking the docstring. So the first thing we're going to do is, again, check for the docstring, but now we're going to focus and actually tell it to continue the visit. So the generic visit call tells it, okay, you've visited the docstring on this node, and now continue down the subtree. And so now we just switch each of these the visit methods that we've defined earlier so that they are calling our visit helper instead. And this time, if we try to attempt the traversal, we now see that we have 4 items that are missing docstrings. And so this was the result that we intended to get in the first spot. So all of the nodes have been visited. And here I have an animation so you can see how the traversal actually looks like at this point. So you can see we're starting up at the top module. And then we go class, function, arguments. And so we're actually exploring all of that tree, but we only do something for the ones that we provided. So this makes sure that, let's say we were only interested in classes, that once we pass the first class, if it has a method and then in that method it has a class, that we would still pick it up. Okay, so one thing we didn't handle in that previous implementation was that it's highly likely that we will have ambiguous names being printed. So imagine if we had named that module or configured it so that instead of saying module is missing docstring, it had said greet is missing docstring because that was the file name, right? Then both the greet method and the greet module would be writing out this exact same message. And to help think about this, and I'm sure at some point you have worked on a code base that had more than one utils file in it, right? So you have a utils file maybe on the outer directory and then an inner directory, and then you would run this tool on your whole code base and you see utils is missing a docstring, utils is missing a docstring, and you have no idea which one. Right? So we need a way to provide unambiguous paths, just like you would have an unambiguous import path to a piece of code that you're using in your library. And the way we have to do this is by using a stack, right? So if you recall from when I introduced the ASTs, from a particular node, we can see its children, but from that node, we cannot see its parent. So we lose the lineage above, which is necessary to make the unambiguous path. So we have to track this ourselves, and that's very easy to do as long as we implement the stack. So to get the stack, we're just going to add an init method to our docstring visitor. You see that we're calling the superclass as init, but we're also taking in the module name this time. And that's because the module node in the AST does not have a name built into it. The other ones do, but that one does not have a name. So we need to provide that ourselves. So we'll ask for the user to pass that in when they instantiate this class. And then we're going to store that so we have it. And then we are also instantiating our stack. So for this example, we're just going to use a list of strings for the stack. So a list of names of nodes that we are visiting. But you can easily extend this to actually, depending on your application, you might want to store nodes in here. Like maybe you want to be able to distinguish methods versus functions. And in that case, you need to know, is that node a child of a class or not? And so you need to know the lineage. Right? It also helps when you're working with nested functions, or perhaps you want to check if the function had a return anywhere. You can't simply check the subtree for a return, because the return could be nested inside of another function that returns, and the outer function doesn't. So there's many use cases where you would want to capture that lineage. But again, we're just going to keep this very simple here and just track a list of the strings. So now we're going to internalize that missing docstring check, because we need to use the stack now to print that something is missing. Right, so here we have detect missing docstring. It takes the same nodes as before. This is the same check as before. The difference is here on this entity line, right? Now, instead of just printing the name of the entity, we are going to use the stack to assemble the path with dots of where this entity is missing. And this gives us the unambiguous name. And then to actually manage the stack, we need to add some additional logic to our visit helper. It's the thing that we do each time we visit a node. So the first thing we need to do is, right when we're being called to visit the node, we need to push or append that node's name to the stack. So here you can see that what I was saying before, that the node has a name attribute, except if it's the module, so that's why that's the default. And so when we first visit the module node, for example, we push the name of the module onto the stack, then we actually visit the docstring, and then we call generic visit to visit the subtree, and then we go all the way down. So that would be the entire tree. Then when we're coming back up, we pop off the stack. So that makes sure that we know that whatever we're visiting is a child of everything on the stack. And nothing else has to change there. And so when we now call our docstring visitor on the AST that we've been working with, we can now see that we still have the 4 entries, but now this time they are unambiguous, right? We have greet, this one here is the module, and this greet is the method that is the greet method. Okay, so now let's take a look at how we can suggest docstring templates based on the code. So we saw function definition nodes and async function definition nodes. I'm going to treat them as the same here because we don't have any async code. They have most of the same properties. And a lot of that information is what you would typically put in a docstring, right? So argument names, types, default values, and that's in the args attribute. The return type annotation, we would typically say what a function or method returns, and that we can extract it from the type annotation if it is there, which is the returns attribute. And then the third thing of interest here is the actual body of the function. So the AST that represents what the function actually does. Now here we're not going to cover that part in the keynote. That is much more complex to actually derive things correctly, but using the stack becomes really handy when you're doing something like that. So this would be maybe you don't have a return value being annotated, so maybe this isn't possible, right? You can look at the body of the function and look for a return node, and then you would know, oh, there is definitely a return in here, and you can potentially extract the type. If you wanted to indicate that you're in the docstring that it raises some sort of exception or that it yields, those are also nodes in the AST, and so you could look for those particular nodes and note that in the docstring. So to keep things more contained and example-wise, we're going to just look at and just write code for fully typed code that we want to extract docstrings from. So in particular, for the next several slides, we're just going to be looking at what would happen for the greet method. So very simple, we have, it's an instance method, we have self as the first argument, and then we have name, which is of type string with default value world, and it returns a string. And you also notice, again, it's very simple. It's one line with some f strings, right? And this is the AST representation of that, right? So we're not going to go through most of these nodes. The thing of interest here is that, so here's our function definition. This side of the tree are the arguments. So that's all stuff we would extract for our docstring. This middle one is the logic of the node of the function itself. So that's that return node you could potentially look for. We're not going to consider this piece. And then the one on the right is going to be the return annotation, which we are going to use. So we're focusing on the left and right branches. So first thing we're going to tackle are the arguments themselves. So if we look here, you see that there's this AST arguments node, and it has all these values. And that's what all these values represent here. And so we have multiple types of arguments that we can specify in a signature. So the first type, which is being represented by the field pos_only_args, are positional-only arguments. So arguments that have to be passed by their position when you call them, and they cannot be passed by name. So this is going to be a list of AST arg nodes. Then we have our args field, and this is now arguments that can be passed by position or by keyword. So they're flexible. And we have the same type. Then we have var arg, which you're probably going to associate with start args. And this is different, right? So this is either there or it's not. So if it's none, if the function does not have that. And then if it does have it, we will have a single arg node that we can work with. So those are the positional arguments. And then the next group we have is our keyword-only arguments, KW-only args. The same type here is a list of arguments. We have the defaults, KW defaults, for this. So these two are tied together. And you'll notice that this is a list. So it's the same size as KW only args. However, if we see a none in there, so something that is not an AST node, that is the way that it's telling us that it is a required field, as in it does not have a default, but it must be passed. So if there is a default, then we will have something here, and it won't be required. Then we have kwarg, which is typically we would see like double star kwargs, and that's going to behave similar to this one. And then the final thing here we have is defaults. And so defaults are the last n positional arguments. So it ties to these two up here. This is a list of AST nodes, but it's not, like as I mentioned, it's not going to be the same size always as the sum of these two. And that is because if you think about how you define a function, once you set a default value, everything after that has to have a default value. So there's room before to not have them, but not after. And so that's the structure behind that. It does make it a little challenging to process it. So if we look at our greet method, we see that we have, just here looking at the arguments portion of the AST, we have two positional arguments, right? We have self, and then we have name. Name has an annotation, which is an AST node, and its ID is string, so this we know is annotated as a string. And then the default down here, you see we only have one default. So two parameters, one default, and this is the default is a AST constant node, and its value is world. So this is the default for this one. So let's go about actually extracting this information into something that we could use in a docstring. So we need our argument names, their types, their default values, and we're going to process this in three groups. So the first group would be our positional arguments, and we need those three fields, the pos_only_args, args, and defaults. Those all work together. Then we have our starred arguments, so that's var arg and kwarg. Again, they're going to have a similar processing. And then the keyword-only args are going to be KW-only args and KW defaults, and those again will be processed together. So to actually do the processing, focusing first on the positional arguments, we're going to use a list comprehension. And we need to make sure that we can account for none, meaning that something is not there, versus none being the actual value none in the docstring. And to do that, we're going to create a sentinel value here, and that's just a no default. So that's telling us that after we've extracted the values, that none is actually a none default versus not having a default. Then for our loop in the list comprehension, we are going to combine both the pause-only args and the args into a single list, and then we're going to reverse it, because we know that from the end, the defaults exist, and then they run out at some point. So we're reversing both that and then the defaults. So those are together. And we're using zip longest from itertools. And so what that does is if you have two or multiple iterators that are of different length, whichever ones run out, instead of causing a stop iteration, it will provide that fill value, which is normally none, but we know that none has a meaning that we want to preserve. So we're going to tell it, when you run out, start emitting no default. And so this means that at each iteration, we're going to have an arg and a default associated to it. And here we have a little hack to keep this simple. So you wouldn't put self or CLS for a class method in the docstring. And so here we're just going to exclude any args that have that name. Now, there are much better and more robust ways to do this. And typically, if you want to do something like this, you would want to use the stack, right? So if you use the stack and you note that you're a child of a class definition node, then you can actually check, okay, you can do further checks. Is this an instance method? And do I see self as the first argument? And then you can confidently ignore that. So once we go through each of the items, or at each iteration, we're going to extract a dictionary that is just going to be a mapping of what we're going to use for our docstring, right? So we have the name of the argument is the arg attribute. The type, we're going to take the annotation that's attached, and we're going to assume that these are going to be AST name nodes, and we're going to attempt to grab the ID from them, which we saw for the string annotation would grab str. If we can't find that, we're just going to put a placeholder. So that will be a signal to the person using this tool that they have to replace that themselves. So we have the name, we have the type, and then the default value. Here we're just checking if the default is not our sentinel value, indicating that there is no default. And if it is actually not the case, that means we do have a default. And we're going to assume that this here is an AST constant node. So if we had actually a default of none, it would be in here, and grabbing its value would mean that default is now none, which tells us the default is none. And otherwise, we're just going to leave the default. So that would be that no default indicator. So we would be able to tell. So the final thing is now we've processed all the nodes, but they're in the wrong order, right? So we need to reverse it so that we have the first argument actually first in this list. So I'm just using slicing to reverse that list. So if we take a look at what this actually does, and also if you haven't seen positional only arguments before, if you add this slash in your function definition, everything to the left of that has to be passed by position. You cannot call this and say function A equals whatever, you will get a syntax error. So if we pass this into our function, and here you can also see what I was saying earlier about calling the AST parse function just on a string of code. So that's why we had to read in the code. So here you can see that it has correctly extracted two arguments, right? We have the first one, a type string, which is correct, right? And the default, this is the no object, sorry, the no default sentinel value, which was the object. Then the second item we have is b, right, which is of type integer, and default 3. So that has been correctly parsed. Next, we can move on to our starred arguments. So here, the only thing we need to keep track of is we want to put a single star if it's var arg, or in a double star if it's the keyword arg. So in order to do that, again, we're using a list comprehension, but we have two fors here just so that we can capture this as a way to tell how many stars that we need. And then we actually grab that value. So that is either going to be an AST arg node or none. So if there's no star args at all in that function, that will be none. So if we do have that argument, then we're going to extract something that looks very similar to before, right? We handle if it's a single star or a double star with this check. We have the same check for the annotation, and there are no defaults here, right? I mentioned that the defaults attribute was tied to positional only arguments, and that the keyword one was tied to the keyword arguments, so these two don't have defaults. So we're just going to put this no default indicator. And then if the arg is not there, we're just going to return none in here. So we will have 2 items being returned from this, a list of 2, and each of the values can either be the dictionary or none. So if we actually call this, and here also to illustrate, so here's that syntax with the single star and the double star. While it's typically the convention to call it star args and star quargs, we don't actually have to, right? So here I'm using extra args and double star extra quargs. And so that's why we needed that function to handle that logic, because it could be anything. So if we run this through our function, we now see, again, we have extracted successfully 2 values. We have our extra args. We don't have the type on these, and so we have the placeholder that we mentioned, and both of these have no defaults. So the final group that we need to process are the keyword-only arguments. So KW-only args, and then KW defaults. So this is now going to be much simpler than the other ones, right? For here, we know that the KW-only args list is going to be the exact same size as the KW defaults list. So we don't have to do anything fancy with zip longest and fill values. We can simply just zip those 2 values together. At each iteration, we're going to have the AST arg node and then its default value. And remember that if it is none, that means that there is no default. So actually extracting it, these 2 are exactly the same as we've been seeing, and then the difference just comes in this area here, right? Because if the default is actually none itself, then that means that it was required, so no default. And again, that is different from the default being none, in which case it actually is an AST node, an AST constant node, and would fall into this case. So this does correctly capture that case. So if we then call our logic on a function that uses keyword-only arguments, and again, if you weren't familiar with this, if you put this asterisk here, everything after this must be passed by name. So now you can't say func1, it will not work, right? You have to say func a equals 1, or a string of 1, right? So if we pass this into that function that we just created, then we can see that, again, we have 2 values being extracted. We have A is a string, it has no default, and then B is integer with default 3. So this is, again, this has been parsed. And so now we would want to put all of this together into our docstring, right? We typically put things in the docstring in the order that we would see them in the function definition. So we need to extract each of those pieces. So the first thing that comes would be the positional arguments. So we call our positional args function, and that gives us back a list of all the positional arguments. The next thing that would come would be star args, right? So we process both of the star arguments, and then we get back to a list of 2 things. We have our star args representation and the double star quargs, okay? And we're then going to check, was var args there? As in, if it's none, there's no sense in adding it to the docstring because it's not there. So if it is there, then we're going to append that node, or the dictionary representation, into the list of arguments that we're going to capture for the function. Then we can move on to the keyword arguments. So we extract those. This is a list that we get back, so we extend. And then the final thing that would go in there would be quargs. So at that point, we can now check if quargs was there or not, and then we can append it to that list of arguments. And at this point, we have all the arguments that we need, and we can simply return the tuple of the args so that we don't risk messing with this any further. So if we were to just call this on the greet method, this would be the result. So it is extracting only the name argument, right? So we had that little bit of logic that excluded self. So here we see that the name argument has the name, the type string, and the default value world. And now we just need to get the return type for this method. And so here, this is much simpler to actually extract. So we have, just looking at the greet method, if we isolated that bit of the AST, we see that we have the returns attribute, and this has an AST name node with ID string. So this is type string. So to actually extract this, we have a very simple function here. We take in the node, whatever it might be, and we're only going to handle two cases. If it's not one of those, we're just going to return the placeholder, which is return type. And that will be up for the person using this tool to actually fix themselves. So here, if it's a constant node, then we want to grab the value attribute. So again, if the return was a none here, this would be an AST constant node where the value would be none. And so this grabs none out, and we can put that in there. And then here, AST name node, so this one here is a name node as it comes in, and so we want to get the ID in that case, like we saw on the previous slide. Okay, so now we have all the pieces for our docstring. We have the parameters, and we have the return values. And so I'm going to assemble the docstring using the NumPy-doc format, the NumPy-doc style, which you can see up here. So we have our triple quotes, we have our description, we have a parameters section where we put the name of the parameter, the type of the parameter, and then the description down here. And then we would have a return section where we have the return type and then the description. And so as a user of this tool, they would be expected to fill in everything with the double underscores around it. So that would be anything that we can't infer ourselves. So to actually assemble that docstring, we're going to create a function called suggest_docstring. And remember, like parameters and all this only applies for functions, so we're not going to worry about modules and class definitions here. So if we are running on one of those proper nodes, then we're going to extract the arguments, so that function that we just created. We're going to pass in from that function node its args attribute. And this is either going to return a tuple of the arguments, which are a tuple of dictionaries, or it's going to return nothing. In that case, we want to just store an empty list, so nothing will be added to the docstring for that. And I'm going to just gloss over the actual logic of how you piece this together because it's not very important for this talk, but again, you have the slides and you can review that. And then for the return section, we would call our return annotation function, and then we pass this the value of the returns attribute on the function, so that return annotation. And this would give us back what it returns, and we just add a description line underneath. And at this point, we now have a list of strings for each of the lines we want to put in our docstring, and we're just simply smashing them together into a single string here. And note that we are putting the triple quotes in there, and that is going to be something that we have to handle with something I'll show you later. So then we just need to make a change to our docstring visitor to actually use this. So in addition to telling the user that there's a docstring missing there, it can provide a hint, like, hey, you might want to use this template to start off your docstring. So that change comes down here. So we're just going to check if it's a function node that we're working with, and if it is, we're then going to print out the suggestion with that docstring. So here, if we call our visitor on the AST once more, we now see for the init method that we have a suggestion of a docstring, right? It has extracted all of this, so it has the enthusiasm parameter that it's type int and default 1. We also have for the greet method, we can see that it has the parameter name, type string, default world, and that it returns a string. But we can actually do even better than this, right? So instead of just telling the user in a printout that it could use this docstring template, we could actually inject those into the code by modifying the AST. So to do this, we have to do a change to how we've actually been doing our traversal. We've been using a node visitor, and the node visitor does not make edits on the AST. So for that, we need to change, and we're going to instead inherit from node transformer. Node transformer does inherit from node visitor, so we've already covered that it will do the traversal correctly, but it just has the ability to actually edit the AST. So our new class is going to be called docstring transformer. And we're going to have a method on here called handle missing docstring. We're only going to be working for the function nodes. And we had pretty much the same logic as before, right? We have our check if the docstring is missing and then provide this and get a suggestion. The difference is that now, because we're going to inject the suggestion in there, we need to mind the indentation of the code, right? We just don't want to inject the docstring flush against the left margin of the code and then have that being highlighted as being incorrect. So to get that indentation level, each node in the AST provides a call offset, and that tells us the indentation of that particular node. So for a function definition, that would be how far indented the D in the def is. And so we're just going to add 4, so 4 spaces further indentation, and then we create this prefix. So this is just going to be padded in front of each line of our docstring. The docstring itself has to be an AST node too, so we need to construct that. We can't just inject a string into the AST because strings aren't directly represented as such. So we need to use 2 nodes here. We need to use an AST EXPR node, and then inside of that, we're constructing our own AST constant node. So that constant node is going to just have the actual docstring text itself. The tricky thing here is that our suggestion included the triple quotes. So if we create our AST node without doing any changes, then when we render this back into source code, we actually will have 2 sets of triple quotes. We'll have the triple quotes we made and the triple quotes Python made to make sure that it was a correct string, and that's not what we want. So we have to have this slicing here, this 3, -3, which removes the 3 quotes on each side. And then we have to actually add the prefix on the bottom line, and that's just because of how text wrap indent functionality from the standard library works. It won't indent a blank line at the end, which is what we actually need. Otherwise, that last triple quote ends up all the way on the left margin, which doesn't work either. So once all of that is properly formatted, that node can then be inserted into the AST. And where would we insert the docstring? Right? We would always put this right underneath the function definition. So we will insert into the body of the function definition. So we take the body attribute from that AST node, which is a list, and we insert at position 0 that docstring node that we just made ourselves. And then the last thing is all of these nodes have, like I mentioned, the column offset, the col offset. They also have a line number that indicates where it's from. That's for use when the code is actually compiled, but we never set a line number in anywhere, right? And so we call fix missing locations, which will add that in automatically for us. And so now we just need to update our visit helper method. It's pretty much what we saw with the other class, with the docstring visitor, right? We're gonna, once we go and visit a node, we're going to handle the missing docstring. Notice we're not using the stack here because we're just focusing on actually changing the code. You can definitely do it though. So we're going to handle the missing docstring. We're going to do generic visit. And then the key thing here is that we are now returning the node. Before we weren't doing that. But returning the node is actually crucial because if we don't return the node, then what happens is each time we visit a node, it gets deleted from the AST, which is definitely not what we want, right? You can't start documenting code that you then delete, right? So we have our 2 visit methods, and both of them now return the result of visiting the node. So that's the way the transformer works. If you visit a node, you can return back either things you want to add to the AST, change about the AST. If you return none, the node is then deleted from the AST. So the final thing now is that we would want to take that code that we've injected and convert it back into, into the AST and convert it back into source code. So one way of doing this is just like we had a parse function that took source code into an AST, the unparse function takes the AST into source code, but with some caveats, okay? So when we do that conversion into the AST, there are a few optimizations that are made, so the code might change slightly. Another thing is that comments are not AST nodes, so they are not represented. So once you read in the AST, the comments are gone. And if you write it back out, the comments are gone. They were never there, right? So that is one thing to be aware of. And the other thing is you'll notice spacing ends up changing a little bit, formatting, blank lines that you had for readability. So here, we're using the docstring transformer. We visit the tree. We unparse the tree. If we look at this, this looks pretty correct, right? We have our class, and the indentation is correct for the function, or sorry, the method of the init method, right? This is a correct indentation. Then the docstring is indented correctly, right? The only thing you might see is that right here, we had spaces around the equal sign before, and now they're gone. So that was just not being represented in how the AST is actually converted back into code. And you will find other subtle things. But we have correctly inserted the docstring into the init method. Again, based on everything we have here, right? We can see everything maps. And also for the greet method, we have been able to represent that entire piece. So the key thing here is that if you are going to do this method of unparsing on your code, definitely make sure you're already in version control or you have the file open and you can undo it in your editor. If you had comments that you were particularly attached to or blank lines, then you will need a way to grab those back. Okay, so at this point, you have some potential next steps for what you could do that extends beyond what we can cover in the keynote. So you could take your docstring visitor and the docstring transformer and remove some of the steps we did before using them, right? So we were reading in the file, and then we were creating the AST, and then we were passing that in. You could configure both of them to receive a file to inspect, and then they can handle reading in that file, making the AST, actually extracting the module name and all of that. You could, as I hinted to before, infer whether there's a return statement there, right? You can see that you have a return annotation missing, potentially, or even check if it's correct, right? Does the return annotation match what the return statement is actually doing? And that would be a spot where you would definitely want to use the stack to make sure that the return that you're looking at is actually the return for that node and not some child node. You could take your docstring transformer and do that conversion that we had at the end, right, where you take the modified AST and then you convert it back into source code and save it to the file for a user. You could also look at supporting configuration, right? You might want to put something in the PyProject TOML or a separate file. You might want to handle inline comments, right? If you've seen there's like those no QA comments or some other ways of telling a particular line that you want that to be ignored by linting, for example. You could do that. And a way to start with that would be the tokenize module in the standard library lets you extract comments. And so pairing that with the AST would allow you to preserve that information. So then you can also think about creating a CLI tool, right? So I mentioned that you would probably want something that runs on multiple code bases. So the easier you make it to use this tool, right, you can apply it in other spots. And so the CLI, you might want to have it run on multiple files. You might also want to turn that CLI into a pre-commit hook. So something that you can make sure that whatever practice you want to run or ensure people are following in their code, that it's streamlined in the process and that people are always running it, right? And so pre-commit hook or a CI tool would be the way to go. Okay, so all of the code that you saw based in here was a simplification of something that I had actually started writing for the keynote. I did make it an open source project. It's called docstringify. So it does this along with several of the things that were our next steps. As I mentioned, I started working on this for the keynote, so it is still very much a work in progress. There are definitely things that I'm looking to tackle, hopefully sooner rather than later, but you're welcome to contribute to that. What's nice about it is that we showed here just NumPy doc style, but once you craft things in a way that it's more modular and you have pieces that are kind of drop-in replacements, it's very easy to support other styles. So for example, in docstringify, I have a NumPy doc converter and then a Google Doc converter. And so it's just very easy to switch it. And if you have your own one, you can also do that. Because all the logic of how do you actually visit each node, how do you detect there's a docstring missing, how do you change it, that's already handled for this other stuff. And so if you want to see how could potentially other things that I didn't get to cover in the keynote be implemented, you also have a reference implementation that you can check over there. Yeah, but so definitely check that out, and I'd be interested to hear any thoughts you have on that. And that is all I had for this keynote. On the left, there's a QR code if you want to send me some feedback of what you thought of this. And on the right, I have links for you to follow my work and to get in touch. As I mentioned earlier, I will put the slides publicly on my website, which is down there and up there. And I will post in the Discord that is there as well. And I will take questions.
Does anyone have questions? Ooh, so I have one.
Hey, thanks. How does AST handle decorators?
So the decorators, we didn't dive into the class definition, but there is actually a separate field where it captures the decorators attached. And then you can use that. So like when I had mentioned checking if something was an instance method or a class method, you can just check actually what it's decorated with. Yeah.
Thank you. It was very interesting. Is it it's working. It's working. Thank you. That was very interesting. I was wondering if you have any other examples of like the cool ways that the static analysis was used. You know, maybe like giving scoring, like readability or stuff like that.
Yeah, so you can even do things like analyze your code. Like maybe you're curious, am I overusing certain things or particular libraries? You can do that. You can use meta programming, like you want to have skeletons and make it easy for people to create their own copies of things. You could do things like updating syntax. So like, let's say you're using a library that then comes with a breaking change and you want to upgrade to that. So you can actually do this to go and find all the instances that use that and then go and change them.
Okay. So also has a lot of experience making linting tools. Linting tools with Python AST, but I see a tendency that rough, you know, the famous linting tool, is like moving more and more out of Python to like more performant languages for all the AST analysis. Have you looked into it? Have you any like experience, opinions on that?
Is the question whether I use rough?
Yeah.
Oh yeah, I definitely use rough. It's very fast.
Did you have an idea of implementing your library as a rough feature?
Well, I don't personally code in Rust, so I would not be able to do that. But I mean, considering the amount of Python tooling that has then become part of rough, like when you think about Flake 8, there's tons of that has then gone into there. So if you make something in Python that is actually very useful, you can kind of maybe sit back and at some point maybe they'll take it over for you. And that would be a great honor too, right? Like that happened with iSort and, you know, to some extent Black, right? That would be a great honor to have that. But that's also why it's so important to use the AST instead of just trying to code up and like import things. Because while you might not be writing it in Rust, you are still getting a speed improvement from writing it, like actually importing and going over things. So it's not as slow as it potentially could be depending on how you write it in Python. You do get that initial improvement.